Now that you know a little bit about motion diagrams and motion graphs, let's take a look at more detail at how to interpret motion graphs. We have three different types of motion graphs we'll be dealing with. We've got position versus time, which we could use an X, Y, or Z to represent our position. We have velocity versus time, and we have acceleration versus time. The general format is on the y-axis, or what we call the y-axis in mathematics, the vertical axis, we'll either put an X, a Y, or a Z, and with our units. So perhaps we're in meters. On our horizontal axis, typically we're working time units of seconds. All right, make sure that you always label your axes with the proper variable and the proper units. So let's take a look at an example. We're going to start by looking at a position versus time graph, and what we're going to do is we'll label our axes, we'll describe the motion, and we'll go through these steps that we have up above. We're going to work on the top third of this worksheet first, then once we complete the top third, we can move to the middle third, and finally we'll work on the bottom third a little bit later. So the first thing we're going to do is label our axes. For this example, we've got this nice blue motion graph. Let's label the axes first so we can decide which direction this is moving and what type of units. And just arbitrarily, I'm going to assume that this is a problem that's moving up and down versus left and right or in and out. And up and down is the y-axis. So we're going to use the y-axis, and I'm going to use feet for our units. No particular reason, just haven't used those for a while. And of course, our horizontal axis we're going to label as the time axis, and we're going to use our MKS units of seconds. Our next step is to actually take a look at each one of these, and based on the shape in our previous exercises, you should be able to describe the motion, in other words, what's happened to the speed and direction of the object over the time in each case. For segment A, for example, well, A is at -2 meters, and over time, it's moved for this 1 second time interval, it stays right at -2 meters. All right, -2 meters. For segment A, for example, we have a horizontal line segment. And what this means is we're at -2 feet on the time axis. At time 0, we're at -2 feet. -2 feet might mean we're 2 feet underground, for example, or 2 feet below sea level, or 2 feet below the top of the table, whatever we happen to define as 0. And we're at this -2 feet for a few moments in time, a whole second. All right, so basically we're stopped at -2 feet for 1 second. So we describe the velocity, which is 0, and the direction, which is not moving at all. For segment B, we're actually moving from -2 feet, and we're moving up to 0 feet. So it looks like we're moving up. And we've got a straight line, so a straight line means we have a constant slope, and we know from before that slope means velocity. Therefore, we're moving at a constant velocity upward. And I'm going to leave it blank for the velocity, so we'll calculate that in a moment. And we do that for 1 second. For part C, we're doing something similar, but this is a negative slope, which means we're going backwards. We're actually going from 0 feet down to -1 feet. So we're moving down at a constant velocity of, we'll fill that in later, and this time we're moving for 2 seconds. In the final situation for part D, this is actually a curve. As we talked about before, a curve actually represents not constant velocity, because velocity is a slope. We have a changing slope. We have changing velocity. So we're actually start at -1 feet, and we're moving up at the end of this up to +3 feet. And if you look at the slope of this, our slope gets steeper and steeper and steeper as we move up. And so it looks like we're moving upward faster and faster. We're accelerating for how many seconds? 2 seconds. All right. I'm going to leave it to you to try out part C. Use the graph to find the distance and the displacement of the object. You should be able to take a look at this graph and figure out how far the objects move in this displacement. And remember, there is a difference between those two. I'm going to skip over to part C, or part D, I guess. Find the slope for segments A, B, and C. Those are the three easy segments. The slope on those are constant. And for segment B, I'm going to show my full work. So I'm going to start on that. For segment B, I'm going to draw a little slope triangle. We actually cross through that point and that point. So I'll just use, here's my rise and here's my run. And here's my work for that segment. Rise over run. In math class, we call that delta y over delta x. I'll put that in quotes because we don't have y and x here. We actually have delta what over delta what. Well, y is our vertical axis, and we actually do have y on this axis this time. But our horizontal axis, our x-axis, is actually t. So we have delta y over delta t. Well, that's just our average velocity in the y direction is what that is. Like we've got a displacement in the y direction over our time. That's average velocity. All right? So let's go ahead and plug in our numbers here. Our rise, which is delta y, is plus 2 feet. We moved up 2 feet. And the run, which is delta t, is plus 1 second. Let's go ahead and plug that in. Positive 2 feet per second. That's my velocity during that time interval for segment. From seconds 1 to 2, we have a slope of positive 2 meters per second. It's a constant velocity. The other ones I'll use a shorter notation. This is a slope of 0. For A, it's a slope of 0 feet per second. For velocity at C, well, we're down 1 over 2, and just got to be careful with scales here. We do have unit scales on both the t-axis and the y-axis, so we can do our little quick counting here. Down 1 over 2 is a slope of negative 1/2 feet per second. So it's moving slowly. The negative sign moves moving backwards slowly. Question now is, what do we do for segment E, the curved segment? So let's take a look at the curved segment here. So for part E, we actually have a changing slope. And so what we're going to do is we're going to look at a few different points on this curve and calculate the slope at each point. So I'm going to pick the points at 4 seconds, 5 seconds, and 6 seconds. I'll just draw a dot at each one of those points. So I'd really like to find the slope at each one of those segments. And the way to do this is on your piece of paper. I cannot do this on a smartboard, but you would lay a ruler down on your curve, and you line up the ruler so it balances on the curve. So for example, I'm going to do the middle point first. The middle point is going to be something like that. All right, and once again, I'm freehanding this. You should take a ruler and balance it on that point and then draw your line in. If you do not use a ruler, and if you do not balance the line properly, you will not get any credit on our quiz or test for doing this, or on a homework. You must use rulers when drawing lines. Don't freehand them. For the bottom point at time equals 4, well, if you look at this and follow your ruler down, you'll find that this is going to be a horizontal tangent. And these are tangents to the point. All right, and up top, if I were to draw a line segment up there, I would have something like that. And once again, you're going to have to, and we can work on this in class, and I can work one-on-one with you if you have a question on this. You need to just balance your ruler on there so that you see an equal angle on either side of your line that you draw, and then go ahead and draw your line, and then you have to calculate the slope of that line. I'm going to go ahead and calculate the slope of the first tangent that I did, which is right here. The slope of that one, I've got a rise of plus 2, and I've got a run of plus 1 second. And so for at t equals 5 seconds, for example, I've got a slope of positive 2 feet over positive 1 seconds, which is positive 2 feet per second. At time equals 4 seconds, that's a horizontal tangent, and our slope of that is 0 feet per second. At time equals 6 seconds, the way I drew my tangent, if you were to count out your slope, you'd find that the slope looks like it's about 4 feet per second. And you might get numbers that are a little bit bigger, a little bit smaller than these. It is what it is. Put down your data. It doesn't have to match exactly mine as long as you're close. All right? I'm going to let you answer part F, and you can tell me in class what you think about part F. So part C and part F, you can come in and we'll talk about that in class and see what you think. the next part of this process is part 2. We've got a nice position versus time graph up above in blue, and we did some analysis on it. We looked to see, we sort of guesstimated what the object is doing in each case based on the shape, and then we actually calculated slope, because the slope of a position versus time graph gives you your velocity. And that's exactly how you're going to calculate a velocity versus time graph. The slope at any point on the position versus time graph represents the what? It's the velocity of the object, of that object at that point in time. So I can take any point in time on the graph above, and for example, for the graph for segment A, at the initial point here, what's the speed? Well, the speed there, it's a horizontal line, it's 0. So down below here, I will plot a 0. All right. Now, if I go like half a second in, well, what's the velocity right there? Well, my slope is still horizontal, so I still have a 0 velocity. So if I go right down at a half a second, down below on the velocity versus time graph, I can plot that point. If I go over to the other end of this line, segment A, the same thing's going to be true. If I go over here, well, my slope is still 0, my velocity is 0. So I can go point by point, look at the slope, and then plot it down below. And of course, for segment A, that slope is constant. It does not change for that second. So we have a constant velocity of 0. And there it is. There's a constant velocity of 0. I have this constant function plotted on my velocity curve. Remember, a constant function in math is a horizontal line. A constant slope up above on the position versus time graph leads to a constant horizontal line on the velocity graph below. We're plotting the slope, the values of the slope. Let's take a look at segment B. Well, for segment B, everywhere on this graph, for segment B, the slope at each one of these points is positive 2 feet per second. It does not change. So we can take those points up above and plot those slopes below. The slope initially is 2. After a moment it's 2, another moment it's 2, another moment it's 2. So we have a constant velocity of 2 meters per second. So a constant velocity in the position versus time graph gives me a constant function down below of that value. Take your velocity up above, plot it down below. For part C, what's our slope along segment C? Well, it's -1/2, -1/2, -1/2, -1/2, -1/2, -1/2. For 2 seconds, it stays at -1/2. So I'm going to go down below. Here we are at time 2 seconds. We started at -1/2. We're still at -1/2, still at -1/2, still at -1/2. We stay at a constant velocity of -1/2. The curve segment's a little bit more interesting because we do not have a constant velocity. We actually have a changing velocity. So if we take at time equals 4 a second, we drew our tangent line. It's a horizontal tangent line. So our slope was 0 feet per second for that horizontal line. So at time equals 4 down below here, we're at 0 feet per second. So I'm going to go right down below, and I'll plot that velocity. Look at the slope, plot it right below. The slope for this point, we're going to plot right down below as well. And what do we find here? All right, and our final point that we plotted up above, we drew a tangent through there, and that's this tangent right here, which we found was at positive 4 feet per second for the slope. Well, that we're going to plot right down below. Now here's 1, there's 2, there's 3, and I'm crossing over to my graph above, that's okay. And here's 4. Here we are, 4 feet per second, right there. All right, so I draw these dots nice and big so you can see. All right, so those 3 dots give us our profile for those 3 points in time. Well, what do you think happens in between? Well, it goes between those points. So they look like they're linear, the way they worked out. And so I'm actually just going to draw a line straight through those. And so if we look at this graph then, so here we are for the first second. For the second second, we're here. For the third second, we're here. And for the fourth second, our graph looks like so. All right, and that's how we create a velocity versus time graph using a position versus time graph. I'll let you go through and answer parts D, E for this process. We're going to hold off on parts F and part 3 for later. So stop right there. Now your homework is to go through, first of all, there's a couple questions you can answer. Do you see any problems with our original position versus time graph? And remember, we were using y in feet versus time in seconds. And what about the velocity versus time graph? Does everything look okay on that? Could we really do that in real life? Is there any issues with that graph? All right, so that's the first thing you're going to have to take a look at and answer that question. It might be good, it might not be. You tell me. And then what I want you to do is I gave you 2 more graphs, and you're going to do the first 2 steps that we did on this worksheet on this page.